So today we're very pleased to have David Knott as the speaker. David is at the National University of Singapore, and he's done loads of interesting work on various aspects of ABC, things including Bayesian synthetic likelihoods, connections between ABC and density estimation, high-dimensional ABC, and links to other methods such as glue and the ensemble Kalman filter. So, David, thank you for joining us, and over to you.
Oh, you're welcome. Thank you very much for the introduction, Dennis, and thanks to the organisers for the invitation to give the talk. So I'm going to talk about distributional regression. Okay, so distributional regression is all about extending conventional mean regression models to model aspects of the response distribution beyond the mean as explicitly depending on features. Okay, so the particular method I'm going to talk about here, it's motivated by the desire to achieve a certain kind of calibration in predictive inference. And the particular kind of calibration we'll consider here actually has an interesting interpretation in the context of regression approaches to likelihood-free inference. So this is a joint work with Nadja Klein from Humboldt University of Berlin and Michael Smith at University of Melbourne. Okay. So let me just give some motivation. So we're considering a regression problem. We have a response Y and some features X, p-dimensional. We have a training set of response and feature vector pairs in observations. And we want to estimate the conditional distribution of the response given the features, at any given value for the features. Now, in a lot of regression models used in applied statistics, we only model the mean response as a function of the features. And I thought I'd share with you this quote from a recent distributional regression paper. The authors take a somewhat militant tone, perhaps justifiably so, and they say the ultimate goal of regression analysis is to obtain information about the conditional distribution of a response variable given a set of explanatory variables. This goal is, however, seldom achieved because most established regression models only estimate the conditional mean as a function of the explanatory variables. So the goal of distributional regression then is to allow aspects of the response distribution beyond the mean to vary with covariance. And there's a lot of different methods for distributional regression around in the literature. Let me just mention a few. There are extensions of generalized additive models to more complex parametric families where you model higher order moments as being dependent on the features through an additive predictor. There are mixtures of regression models of various kinds. There's a lot of nice methods in the Bayesian non-parametric literature. There are finite mixtures of regression models like mixtures of experts, quantile regression and Bayesian variants of that, quantile regression forests, and conditional transformation models and normalizing flows. So why does the world need another distributional regression method? Well, I think it's fair to say that many current distributional regression methods, they don't scale well to either large N or a large number of features or both. So before I proceed further though, I think it's a good idea to explain why I'm talking about distributional regression at an ABC seminar. So one approach to doing likelihood-free inference uses regression. So suppose I have a parametric statistical model for some data D with parameters rho. I set up a full probability model through a prior density, say, on the parameter rho, and a sampling density for the data given rho. Then the posterior distribution is just the conditional distribution of the parameter given the observed data in this joint model. So regression is just conditional density estimation. So I could simulate n pairs of parameters and data from this joint model. I could fit a distributional regression model with the parameters as the response and the data or summaries of the data as features. And then in that regression model, I can get the predictive distribution at the observed data as an estimate of the posterior distribution. Now here, for simplicity, I've just talked about simulating data from the prior, but you can do something slightly more clever if you had, say, a pilot estimate of the posterior. Let me just explain the goals of this talk then. So I want to develop a scalable distributional regression method that's, in a sense, a very minimal step beyond deep neural network mean regression models. The motivation for this semi-parametric approach I'll talk about is concerned with achieving a certain kind of calibration in prediction, something called marginal calibration. And that has an interesting motivation in likelihood-free inference applications. And in principle, I'm using deep neural network basis functions in our construction here. In principle, you could use other kinds of basis functions. But later on, I'm going to talk about likelihood-free inference for time series, where the feature vector is a time series, possibly a long time series. And the clever dimension reduction capability of convolutional networks are going to be useful here. And that's an observation that's been made by others as well. Right, so now I don't know much about deep learning, but let me just give you a brief introduction to mean regression with deep neural networks. And then I'll talk about some of the ways that people are trying to improve uncertainty quantification in deep neural network regression models. And in a sense, our method is an addition to that literature. So a deep neural network, it's just a flexible parameterized function, f eta x, say. So eta are some learnable parameters called weights. X, of course, is the feature vector. And in a regression context, I might want to use a deep neural network as the mean function in a regression. Okay, so here I'll just be concerned with a univariate response. So my deep neural network will have a scalar output. And a deep neural network, it's defined through a composition of functions. The component functions, they're called layers, and outputs from one layer feed into the next. So here's a graphical depiction of a vanilla feed-forward neural network. So we have our inputs on the left here. That's our feature vector. The vertical rows here in the graph, they're the layers. At each layer, you have a linear projection of the inputs from the previous layer, and then that is passed through some kind of non-linearity. And then on the right over here, you have the output. Okay, so there are many different kinds of architectures for deep neural networks, such as convolutional networks, recurrent networks, and so on. And later on, I'll be using a convolutional network, which is useful when the feature vector is in the form of, say, a time series or an image or something like that. Now, deep learning regression models, they are usually trained by minimizing some kind of empirical loss function with respect to the trainable weights. Okay, so most commonly in regression problems, you use a squared error loss like this. The minimization is usually done using stochastic gradient descent. You can also add an explicit regularization penalty to that empirical loss to help prevent overfitting. But regularization in deep learning can also be implicit. It can be implicit in the way you do the optimization itself. So you can do early stopping. It can be important how you initialize the optimization. And there's different ways you can alter the optimization to impose some sort of regularization. Now, if I had, say, a squared error empirical loss, and I had an appropriate explicit penalty, you could think of minimizing the penalized empirical loss as being equivalent to Bayesian posterior mode estimation in a constant variance Gaussian model. Of course, the minimization of the empirical loss has a justification that goes beyond a certain parametric model. But now, that correspondence, it suggests a very naive approach to uncertainty quantification that you do see sometimes. So after you've trained your deep neural network regression model, if you can estimate the variance in some way, you can just plug in your conditional mean and variance estimates into a Gaussian density to give a Gaussian predictive density. But understandably, researchers want more sophisticated uncertainty quantification in some problems. Okay, so there are two basic strategies in the literature on uncertainty quantification for deep learning. So you might follow a strategy of what I'd call a model-based approach. So here you use neural network components as predictors of parameters, say in some parametric model for a response in regression. So there's things like mean variance networks, where both the mean and the variance are modeled using neural networks. So you can use a Gaussian distribution for the response. There's things like mixture density networks. There, the response distributions are a mixture with normal components usually. And you can model the mean and the variance in the mixture components through neural networks and the mixing weights as well. There's also deep versions of quantile regression. An alternative to that sort of model-based approach is a more modular approach based on some kind of post-processing adjustment. So a lot of the existing work on post-processing adjustments, it's for classification problems rather than regression. But there's some existing work on calibration for uncertainty quantification for regression. And in fact, it's something of a hot topic right now. So the field is moving quite fast. One advantage of the post-processing approach is that it's modular and it's computationally cheap. So the post-processing happens in basically the same way, no matter what neural network you fitted in the first stage. Okay, so a lot of existing methods for sophisticated uncertainty quantification in deep learning are inspired by notions of calibration in the literature on probabilistic forecasting. Okay, so there was a very influential paper by Knighting and Raftery in RSSB some time ago, and they proposed a framework for probabilistic forecasting that was based on the idea of maximizing sharpness subject to calibration. So sharpness refers to the amount of uncertainty in the forecast, and calibration refers to some sort of statistical consistency between the forecasts and the observations. So a lot of the early work on probabilistic forecasting happened in meteorology. So there's two basic kinds of calibration. So a lot of the literature on uncertainty quantification in deep learning has been concerned with the idea of probability calibration. And so Basically, for probability calibration, the idea is that events that are given probability P by a forecaster, they should occur with a relative frequency of P. So in practice, if you're checking probability calibration in the regression context, this amounts to looking at probability integral transforms and checking for uniformity. So in a regression context, say you have a set of responses. For each response, you have a predictive distribution function. You can transform the response by the predictive distribution function. You can look at the empirical distribution of those values, those so-called probability integral transform values, and that should be close to uniformity in order to have this property of probability calibration. Marginal calibration, it is basically the idea that the average forecast distribution should equal the empirical marginal distribution. There are slightly different ways to define these concepts, actually. But an ideal forecast is both probability and marginally calibrated. Now, calibration isn't enough to have a good probabilistic forecast. You can have calibrated forecasts that are terrible. In general, forecasts with less uncertainty are more useful, but they have to be calibrated to reality. Okay, so a lot of this literature on probabilistic forecasting and calibration is in the literature on time series forecasting, but here we're considering forecasts in the form of regression predictive distributions. Now, as I said, a lot of work on uncertainty quantification in deep learning has been concerned with achieving probability calibration. So this, the method described in this paper is one that I'll benchmark against later. And they suggested a probability calibration technique for regression post-processing adjustment. And in their paper, they have this quote that I thought I'd share with you. They, as I said, focus on this notion of probability calibration, but they discuss other notions of calibration as well. And they say that we found that the notion of marginal calibration was too weak for our purposes, since it only preserves guarantees relative to the average distribution. The goal of this work is actually to explore marginal calibration. And we somewhat disagree with that quote. And at least in some problems, marginal calibration and imposing marginal calibration on predictive distributions in a regression model, that's a useful complement to probability calibration. Okay, so how do we come up with a regression technique where we have the marginal calibration property that we seek? Well, we use a method based on copulus. Okay, so the idea is that we'll estimate the marginal distribution of the response empirically from the training data, and then we'll somehow ensure that that empirically estimated marginal distribution is built into the model. Okay, so we're going to use a construction based on copulus. For those of you who don't know much about copulus, a copula, it's a multivariate distribution with marginal distributions that are uniform on the range 0 to 1. And you can represent any multivariate distribution by specifying a copula and a set of marginal distributions. And that's a consequence of Sklar's theorem. And copulas are very popular in multivariate modeling. And the reason is that use of copula representations that allows you to think about marginal distributions and modeling dependent structures separately. And here we're going to be concerned with continuous distributions. And for continuous distributions, the copula is unique. And we're going to use something called an implicit or inversion copula. So if you take a multivariate continuous distribution and you extract its copula, that's called an implicit or inversion copula. And the idea is that we could couple this copula with basically any kind of marginal distribution we like. And so what we're going to do is we're going to use an empirically estimated marginal distribution for a response, and we're going to couple that with an implicit copula that we get from a deep neural network regression model. So we're defining some sort of copula on the feature space. Okay, so in a bit more detail, this is how our model works. So let's write a y for the vector of the n responses. I'm going to write x for the set of all the features for the n responses. So yi is the ith response, xi is the corresponding feature vector. Let's look at the let's define a conditional density for y given x based on a copula decomposition. So in this expression here on the right-hand side here, f of yi given xi, that's the marginal distribution for the ith response given the ith feature vector. P of yi given xi, that's the corresponding density function. And this function, C dagger here, this is the density of a copula, okay? And we're going to specify the density of our copula as the implicit copula of a deep neural network regression model. And we're going to specify these marginal distributions for the responses here as being feature invariant and all equal to a marginal distribution of the response obtained just via a kernel estimate. So it might seem a bit strange to make the marginal distribution for the responses invariant to the features. But the features are in the dependent structure in the copula, okay? So, you know, if you look at, say, the predictive distribution for a new x, not in the training set, then the predictive distribution at a new feature value, that is a function of the features through the copula, okay? So if you want an analogy that would help you understand this, think about, say, Gaussian process regression. Okay, so in a Gaussian process regression, we can have a prior on the mean function that's stationary. In that case, the marginal is invariant to x. But of course, once you condition on data, the predictive distribution depends on x. Okay, it's similar here. So even though our marginal distribution is specified as invariant to the features in the model, once you condition on data, when you look at predictive distributions, because of the dependence in the copula, there's dependence of the predictive distribution on the feature through that. Okay. So, so the marginal distribution of the responses, the empirical marginal distribution of the responses, it's going to be sort of built into the model in a sort of empirical based fashion. And then let me describe now how you'd construct this implicit copula in the regression. So to obtain the DNN implicit copula, what we do is we consider a deep neural network regression for some transformed responses. So we transform the raw responses y to approximate, so that the transformed responses are approximately standard normal. Then with these transformed responses, we fit a deep neural network regression model. In the deep neural network regression, the nodes, the last hidden layer, they define some basis functions. And then we're going to use those basis functions as features in a regression model where we use a conditionally Gaussian prior on the coefficients for the features. And then when you integrate out the coefficients over that conditionally Gaussian prior, then we use the correlation function of that Gaussian process if you like, to define our copula. Okay, now the copula there, it's depending on the parameters in the prior on the coefficients. Okay, and once you integrate out the hyperparameters, the copula here is no longer Gaussian, but we have this kind of conditionally Gaussian copula. And that's computationally convenient, but then we get a non-Gaussian copula once we integrate out the hyperparameters in the coefficient prior. Okay, so let me first of all talk about a simple example, then I'll move on to some likelihood-free inference applications. So I'm going to talk about the Boston housing data. So my apologies for using such an old data set, but it's well suited, actually, this data set to showing off the features of our methodology. Okay, so the Boston housing data, you have a response that's median house price measured in some neighborhoods in Boston. You've got some features related to information about the neighborhoods, and the goal is to predict the median house price. And for this particular data set, the response has a marginal distribution with very complex features, and that makes this data set well suited to, as I said, showing off some of the features of our methodology. So I'm going to show you now that our deep neural network Copula regression model, it provides good uncertainty quantification in prediction here. So in the paper, we look at some data splitting and some evaluations of predictive performance using scoring rules. And the deep neural network Copula approach, it does outperform a naive deep neural network approach, as well as a deep neural network approach with probability recalibration. So let me show you some graphs anyway. Here's some two graphs that shows you some calibration properties of different distributional regression methods for the Boston housing data. So the plot on the left, it's examining probability calibration. So as I said, the way you check probability calibration empirically is by looking at probability integral transforms for the responses and then seeing if those are uniform. Okay, so for our responses, we can transform them by their predictive distribution functions. That gives us these probability integral transform values. We can look at the empirical distribution of those, and that empirical distribution should be roughly uniform on 0, 1. So you can look at a difference between the empirical distribution of the probability integral transform values and the distribution function of a uniform on 0, 1. And so that's what this plot is showing. And so if you have a deviation from 0 in this plot, that's indicating a lack of probability calibration. So the yellow line here is for a naive DNN approach using a plug-in Gaussian predictive distribution. So the naive DNN approach has poor probability calibration. The purple line, that represents a probability recalibration of the naive DNN using a certain method that's known in the literature. So the recalibrated DNN, that has good probability calibration. It's bound to have good probability calibration by construction because the method is designed to achieve good probability calibration. For our Copula approach, we have two approaches corresponding to two different priors on the regression coefficients in the implicit Copula construction. Okay, so the blue line here is the deep neural network Copula approach with a ridge prior. That doesn't have very good probability calibration, but we also have a deep neural network Copula approach based on the horseshoe prior. So the horseshoe prior has, as you know, it's a commonly used sparse signal shrinkage prior where there's a scale mixture of normals representation. So we're making use of that here to get the conditional Gaussian prior we need in our implicit Copula construction. So this brown line is for the deep neural network copula with the horseshoe prior, and that has pretty good probability calibration. The green line is a mixture density network approach. So a mixture density network, that's we considered a method where the response distribution is a normal mixture with two components, Gaussian, and the component means and variances modeled by neural networks, and the mixing weights also. The plot on the right here, that's examining marginal calibration. So here you want to see whether the average forecast distribution, the average predictive distribution, is similar to the marginal distribution for the response. So we have the same methods. So the bars are a histogram for the observed response values. We've also got a kernel density estimate, that's the gray line. These, again, the blue and brown lines here are the deep neural network Copula approaches. They do a pretty good job in terms of attaining marginal calibration here. The other methods are not so good in terms of their marginal calibration properties. So for our method, particularly the deep neural network Copula approach with the horseshoe, it is pretty good at achieving both probability calibration and marginal calibration. Now let me show you some predictive densities from some of these different methods. And the purpose of showing you this is just to show you how the Copula method, the shape of the predictive densities adapts in quite a complex way depending on where you are in the feature space. Okay, so in these graphs, in each graph, the blue bars, they're a histogram of the observed responses. I've got a kernel estimate, that's the sort of brown line there. And the yellow line is the average predictive distribution. And the sort of individual curves you see, they're predictive distributions for 100 different observations of the response. So we take the feature values for 100 different observations and we're plotting their predictive distributions. So here at the top left, this is a naive deep neural network. There we just have a plug-in Gaussian predictive distribution. As you can see, these predictive distributions, they only vary by the location. So there's no adaptivity of the shape of the predictive distribution to the features. Here is the probability recalibrated version of the naive deep neural network. And here the predictive densities, they're now non-Gaussian, but again, there's not much variation in the shape of those predictive distributions over the space. Now, a mixture density network, that's a very flexible density regression method. As you can see, there is a adaptation of the predictive distributions to the features. You get very complex and different shapes at different points in the feature space. That's also a feature of the predictive distributions you get using the Copula approach. Okay. So our method does achieve, quite a bit of flexibility in the predictive distributions. I must say it's not a method that has a universal approximation property. So the Copula approach, it's a semi-parametric approach, but nevertheless it's flexible and it often improves uncertainty quantification in some of the applications that we've looked at. Okay, so let me come back now to likelihood-free inference applications. So I mentioned before that distributional regression methods, they're potentially useful in the context of likelihood-free inference. The idea is that if you have some joint Bayesian model specified through a prior on a parameter and a sampling density for data given the parameter, we can simulate parameter and data set pairs from the joint model and then use a regression to empirically estimate the distribution of the response given data or summaries of the data. and then a predictive distribution from our regression model to estimate the distribution of the parameter given the observed data. That's an estimate of the posterior distribution. And our regression Copula approach, it is motivated by a desire to achieve marginal calibration. And in the context of likelihood free inference applications, there's a good motivation for imposing marginal calibration on our regression approximations. And the reason is that if you look at the average posterior distribution, averaging over data sets drawn from the prior predictive, the average posterior distribution will be equal to the prior, okay? And the prior was, that's the marginal distribution for the responses in our regression. So it will turn out that imposing a marginal calibration on our predictive distributions in regression is going to correspond to imposing a property that holds for the true posterior onto our regression approximations. Okay, so let me elaborate a bit more on this. So in our regression, we trained it with data that was basically sampled from the prior predictive. So for data like that, if I look at the average of the posterior distributions, then that, for n large, that's going to be approximately this expectation where I integrate the posterior given data D over the prior predictive for D. And of course, the integrand here, this is just our joint Bayesian model for rho and D. We're marginalizing over the data. When you integrate out D, you just get the prior distribution for rho. So the average posterior distribution is just equal to the prior here. As I said, here I'm considering data simulated under the prior. If you had some sort of pilot estimate for the posterior for the observed data, you could also truncate the prior to the region of effective support. And this would all go through as well. Okay, so that's for the true posterior. So the average posterior will be equal to the prior if we repeatedly sample data from the prior predictive. Now let's replace the true posteriors there by regression approximations to the posterior. So I mean, we might want to, if your regression approximation to the posterior was accurate, then you would hope that this holds, okay? If I replace the posteriors here by their regression approximations, this average should be approximately equal to the marginal distribution for our responses in the regression, which is the prior. Okay, so marginal calibration for the training sample in our regression method, it just corresponds to this marginal calibration property. Now, I should make the point straight away that if your regression approximations aren't calibrated, then they aren't accurate. But if your regression approximations are calibrated, that is no guarantee that they are accurate. Okay. For example, say I decided I would always approximate the posterior distribution by the prior. That would be a marginally calibrated procedure, but it would give you terrible approximations to the posterior distribution in general. So imposing marginal calibration on a regression model, it's not guaranteed to give good distributional approximations, but we do find that it does improve uncertainty quantification markedly empirically in many examples. I should say also that notions of probability calibration have been used for assessing conventional ABC approximations. So both for checking that approximations are accurate or at least not inaccurate, as well as for making adjustments. Now I should mention, earlier on I talked about some different distributional regression methods in the literature. there's been a lot of work specifically on distributional regression for likelihood-free inference. So there's methods based on quantile regression forests, orthogonal series estimators, mixture density networks, methods based on normalizing flows, or copulas for estimating summary statistic likelihoods. So this is a direction of research that's been already pursued by many others. But our method is a little different in that it's a scalable semi-parametric method. They're scalable to both large N and a large number of features. And it's motivated, as I said, by this marginal calibration property. It has a motivation in the likelihood-free inference context. So let me talk about one likelihood-free inference example for a time series model. The model I'll consider here, it was described in a paper by Faziolo and Wood. Their model, it's based on an earlier model in this paper by Turchin and Elmer. So the data is concerned with some trapping data on voles abundances from Finland. So here's the data. This figure is from Faziolo and Wood. And the time series here, it's a time series of a trapping index. So you have a measurement for spring and autumn for each year for 45 years. So you've got 90 observations here in total. This trapping index, it's a count of how many voles were trapped divided by, in each time period, divided by some measure of the amount of trapping effort made. And the measure of the amount of trapping effort made is actually missing for a part of the series. And Faziolo and Wood, they consider certain adjustments to the data here that I won't describe right now, but you can find details in their paper. The model I won't describe in detail, but I'll just talk about the general framework of the model. So it's a continuous time stochastic differential equation model for scaled abundances. So NT and PT are going to be abundances at time t of voles and weasels, respectively. So weasels are one of the main predators of voles. And in this model, it has 9 parameters. There are 2 intrinsic growth rate parameters for the voles and weasels populations. The growth rates vary seasonally. So there's a seasonal modulation parameter. In the model, there's a separate treatment of the weasels and other generalist predators. So there's 2 parameters that sort of describe the behavior of generalist predators and 2 parameters describing the behavior of the weasels. We don't observe the abundance for the weasels directly. So we assume that the trapping data is a sampled version of the abundance, and there's some sort of sampling rate parameter phi, and there's a standard deviation of the driving Brownian motion in the model. Okay, and so for simulating from this model, we use the SYN-like package of Faziolo and Wood. Now we're going to use our Copula approach here using an implicit copula of a convolutional network. So I'm not going to describe convolutional networks, but they're neural network architectures that are very convenient for structured feature vectors that might take the form of a time series or an image. Okay, so here we have a parameter vector rho for our model. We've got 9 parameters, and we've got a time series for our data, a time series of length 90. And then what we can do is we can simulate from the model parameter and data set pairs. So each simulated data set here is a time series of length 90. and we're going to use the whole time series as the feature vector in the regression. Okay, so in this approach we're considering here, where we just use the whole feature vector, the whole time series as a feature vector, we don't need manual specification of summary statistics here. Although, I mean, of course, there are some tuning parameter choices that need to be made in the convolutional network architecture, but those choices are not so difficult to make. Okay, so we're going to, we simulated 10,000 different data sets here. We use 8,000 data sets for training and 2,000 for testing. Okay. We're going to benchmark our Copula approach against some other methods. We're going to use a naive DNN approach. We're going to use an ABC approach with heteroscedastic neural network adjustment. We'll use the implementation in the ABC package and use the summary statistics that Faziolo and Wood considered in their paper. For choosing the tolerance in the ABC, we tried to put a bit of effort into doing that. We use cross-validation to choose the tolerance parameter. We're going to compare our Copula approach with a convolutional network with the Copula approach with summary statistics. Just to sort of get some idea of whether it's the use of a convolutional network or the Copula approach that's giving a gain here. And we also look at quantile regression forests implemented in the ABCRF package. And again, we tune tuning parameters in the approach using cross-validation. And you know, for looking at the real data, we also looked at some Bayesian synthetic likelihood-based approaches. So I won't show you any tables here. I'll show you a graph in a minute, but the deep neural network Copula here, it does generally outperform the other methods with the smallest mean squared error values on the test set data sets, and the coverage rates are closest to the nominal levels. The random forest also performs pretty well, but it has a bit more conservative uncertainty assessments. The deep neural network Copula, it outperforms the approach based on summary statistics. So certainly the use of the convolutional network and avoiding summary statistics specification here, that's helpful. Also, pretty much all the methods here calibrate quite well marginally, except for the naive DNN method. Okay, so here's a plot just examining the marginal calibration in this example. So we've got a plot for each of our 9 parameters in the model. Again, the blue bars represent a histogram of our training set responses, which are simulations of the various parameters from the prior. And the different methods are shown here in this graph down the bottom. So the brown line is the Copula approach, purple is the ABC random forests, and the yellow is the DNN. So the ABCRF and the ABC here, they're virtually indistinguishable. So the only method that's really not well calibrated marginally is the naive DNN method here. And of course, our Copula calibration fixes that lack of calibration and does give better uncertainty quantification. So here we're looking at calibration for, you know, and how we perform in getting the posterior for data sets, new data sets simulated under the prior. You can also consider some sort of, for the observed data, which is a time series, you could consider some sort of data splitting within the observed series and see how well you perform in forecasting. And there's also some comparisons of that kind in the paper. So I just want to wrap up with by saying a little bit about future directions. So the idea of using marginal calibration to improve a regression model is quite a general idea. You don't necessarily have to use it just with deep neural networks. Here I've focused on estimating marginal posterior distributions, but you could, of course, you may want to estimate the joint posterior distribution, in which case you need multivariate distributional regression approaches. One way to do regression with a multivariate response is to try and reduce multivariate regression to a sequence of univariate regression problems. So for example, you could consider likelihood-free Gibbs sampling, where you try and approximate full conditional distribution area with regression. Or you could sequentially order components somehow in the parameter. And so marginal calibration, it's well motivated in those kind of approaches also. I'm running a bit short of over time, so maybe I'll just skim through this very briefly. But if you consider simulating parameters and data from your joint Bayesian model, and if you consider the full conditional distribution for a certain component of your parameter vector, if you look at the average of the full conditional, averaging over the training observation values you would use here to estimate the jth component of the response conditionally on the other parameters in the data, the average full conditional distribution is equal to the marginal distribution for the prior. Okay, so this marginal calibration property, if you imposed it on a regression approximation, estimating full conditional distributions, that may be a good idea. And a similar remark holds too if you consider a sequential decomposition of a posterior distribution using an ordering. Okay, so that's all I want to say. If you want to learn more about this work, most of the references I've given and more details are in our paper, which has appeared online now at the Journal of Computational and Graphical Statistics, and there's a preprint version available on the archive. Okay, so thanks very much for your attention.
Okay, that's brilliant. Thank you very much, David. So moving on to questions now. We had a question in the chat from Christian right at the start of the talk. So
yeah, I shouldn't have ignored that. Okay, are all distributional regression models fully specified? Okay, so I guess by that question you mean, are there methods that are where you just specify, say, models for some moments, is it? But you don't specify a full probabilistic model, is that the idea? Yes, like quantiles. Yes, certainly there's quantile regression methods, even Bayesian ones. So there are a few papers about quantile regression in deep learning. So potentially, you could use quantile regression in likelihood-free applications. If you have a particular focus, say, on just estimating credible intervals or things like that, you could do that in a very direct way. Perhaps making weaker assumptions by just using a quantile regression approach. I think probably that's been done, but probably quantile regression has been used in likelihood-free applications before, but I'm not sure. Does anyone know about that? I think I'd be surprised if that's not been explored before, but I don't know of any work along those lines.
Okay, so do we have any other questions? So I have, Christian just replies to you saying he doesn't know about quantile regression. So I agree that I've got some sort of vague memory of seeing a paper that's done this, but I can't be 100% sure.
I have a feeling that perhaps David Balding and some of his co-workers has written a paper about this, but I like you, I think I've seen something, but I just can't quite remember.
Michael has his hands up. Michael, go ahead.
Hi, David. Many thanks for the interesting talk. I would like to double check whether I correctly understood the construction of the implicit copula or the CDNN. I think you used it in on your slides.
Yes.
So was it that first you fitted the neural network, then you extracted kind of you froze it and you took the activations of the last layer as your fixed features.
That's right.
And then used like Bayesian linear regression essentially with those features as covariates.
Yes.
So, and from out of that, you then extracted the copula by kind of getting rid of the marginal of the posterior predictive.
Yes, you have a conditionally Gaussian prior on the coefficients.
Mm-hmm.
And then when you integrate out the coefficients according to that conditionally Gaussian prior, then basically you have some sort of fixed rank Gaussian process then where you have some sort of adaptively learned features that you learned in the original stage.
Okay, and the extraction of the copula is possible because you know that the marginal posterior predictive is, you can kind of read it out what the correlation structure is.
Yeah.
Okay.
Yeah. So it's kind of, yeah, that's right. Yes,
Okay.
you understand correctly. Yes, that's right.
Okay, thank you.
So I had a quick question about the features that you're extracting from the neural network.
Yes.
So since the neural network is, the loss function is looking at just a kind of mean regression, is there a danger that these features will mainly pick up features that are relevant to that, and you may not pick up some relevant information about distributional regression?
That's a good question. So that's what you say when you don't have a good answer. It's a good question. Yeah, so I guess the motivation for that construction that we used, it sort of comes from a method that's called a Copula Process in machine learning, and there's similar ideas to the Copula Process in the spatial statistics literature as well. And so in the Copula Process, you sort of have a Gaussian process with, say, a normal 0, 1 marginal, and then you can transform the marginal to uniformity, and then you can transform from uniformity to any other marginal distribution you like, just using the distribution function that you want. And so, the way we constructed the basis functions, it was based on the idea that we're going to specify a Gaussian process, at least conditional on some hyperparameters. And so for a Copula process, it's like a marginal transformation of a Gaussian process. So we sort of transform so that the responses go back to standard normal approximately. And then, for that Gaussian process, you'd want to try and estimate a correlation function. And so we estimate the correlation function through a deep neural network regression with these Gaussian priors on the coefficients, and then you integrate out the coefficients. That gives you a Gaussian process. So, so yeah, I think your concern is perhaps a valid one. So, our method, it's sort of a way to come up with a sort of data adaptive estimate of a correlation function for a Gaussian process. But is the way we train the regression model, is that flexible enough to get complex features of the distribution? There may be better and other ways to do it. So yeah, that's a good question. I don't really know.
I mean, it does seem to do pretty well on your example, so it's...
Yeah, it does seem to work well in practice, but I'm not saying that you couldn't change that aspect of the recipe and get in a clever way and get better results. Yeah.
Okay, thank you. Do we have any more questions? Okay, so it looks like that's it for the questions. Thank you everybody for coming. Let's thank our speaker again, David. Thank you very much for being with us today.
My pleasure, thank you. Okay, so I'd like to thank the organisers very much. This is a really great initiative to have this seminar series. So yeah, I enjoyed it. Okay, so good night or good morning.